Now we are going to see the computation of expectation by conditioning. Okay, and it is a very important and useful technique in probability and in many other places like stochastic processes, statistics, and many places. Okay, so what do we mean by the computation of expectation by condition? Before going into the theorem, the next theorem which says that expectation can be written as expectation of x given y. Let us first discuss what do we mean by expectation of x given y. Okay. So what we have seen till now is that the conditional expectation of x given y for the continuous random vector xy and for the discrete random vector xy. Okay. So we have seen that for the discrete random vector, the conditional expectation is given by summation of x f of x dx. Sorry, for discrete random vector, the conditional expectation is summation over x into the conditional probability density probability mass function, and for the continuous random vector, it is the integration of x times conditional probability density function dy. Okay. So now notice that when I do the sum over here with respect to x with over appropriate support, then this quantity is a function of y. Okay, so if I change y, this quantity will change. But x, when I take the sum over x, x will go away, only y will be there. Similarly, in this case also, when I do the integration with respect to x, I am sorry, this will be x. When I take the integration with respect to x, the y will remain there, and if I change y, this value will change. Okay, so that means in both the cases, the conditional expectation of x given y equals to y is a function of small y. Clear? So that means that that's what I have written here, that the conditional expectation is a function of y. Okay, the conditional expectation of x given y is a function of y, and in that means that if I call that function as g of y, if I call this function as g of y, now depending on different value of y, this expectation takes different values. So that means the function I denote by g of y, and in that case, if I write g of capital Y, that is a function of random variable y, right? This expectation of x given y equals to y is a function of small y, which I am writing as g of y. Now I am considering g of capital Y. Clearly, g of capital Y is a function of y, and that's why g of capital Y is a random variable. Yeah. So g of capital Y, which is generally denoted by expectation of x given capital Y, that equals to y, this equals to y part is missing here. So that's what we write normally, that g of capital Y is same as expectation of capital X given capital Y. So this quantity is a random vector. Sorry, this quantity is a random variable, right? Because g of y is a function of y is a random variable. So this is this g of y is a random variable, and g of y generally denoted by expectation of x, capital X given capital Y. Okay, so that means if it is a random variable, I can talk about the expectation of this random variable. And this theorem says that the expectation of x can be written as expectation of this random variable. Now notice that when I am writing here two expectations, the inside expectation is the expectation with respect to the conditional distribution. Okay, so I will find out what is the conditional expectation of x given y equals to y, and then I will replace small y with capital Y to get expectation of x given y. And to do this one, obviously this expectation is basically the with respect to the conditional probability mass function or conditional probability density function, depending on whether xy is discrete random vector or xy is discrete random variable. Now, for the outside expectation, you see that this dy is a function of y. So this quantity is a function of capital Y. Being this one is a function of capital Y, the outside expectation is with respect to the distribution of y. Okay, so expectation of x can be written into the into the two expectation. The inside expectation is the conditional expectation with conditional expectation, the inside expectation with respect to the distribution of conditional distribution of x given y, and the outside expectation is marginal expectation with respect to the marginal distribution of y. Okay, here the proof I am coming into, but before proof, just take an intuitive idea of what this theorem is. And the intuitive idea actually comes from what you have done or we have done in the school level. So suppose in a class we have three columns of benches. Okay, just like many lecture hall complexes, many lecture halls we have in IITG. So what I am assuming that three row of benches are there, and maybe that teacher is standing here and students are sitting on benches in three columns. Okay, now we assume that the first column has n1 students, n2 students for the second column, and n3 students for the third column. And suppose I am talking about the average height of the students, and suppose x1 bar is the average height of the student who sit in the first column. x2 bar is the average height of the student who sits in the second column. Similarly, x3 bar. Okay, in this case, using the class school level mathematics, you know that if I try to find out overall average, which is x bar, which is nothing but n1 times x1 bar plus n2 times x2 bar plus n3 times x3 bar divided by n, right? That we know from the class level mathematics, school level mathematics. Okay, so now notice that this one I can write as n1 by n times x1 bar plus n2 times n by x2 bar plus n3 times n by x3 bar. Okay, that's why I can write. Now see what we are doing here. What is x1 bar? x1 bar is basically average height of the student sits in this column. So that is basically the conditional expectation. The conditional expectation of the height given the student in the first column, right? Similarly, x2 bar is the conditional expectation of height given the student in the second column, and x3 bar is the conditional expectation of height given the student in the third column. Yeah? So x1 bar, x2 bar, x3 bar, they are basically nothing but the conditional expectation, and that xi bar is the conditional expectation of the height given the student in the ith column. Okay. Moreover, what is this n1 by n2? Sorry, n1 by n. This is nothing but probability that a student is in first column. Is in the first column, right? Similarly, this is the probability that student in the second column. This is the probability that is student in the third column. So what is this quantity? This quantity probability multiplied by the conditional expectation. So that means I can write from here. This is nothing but summation probability student in ith column, multiplied by expectation of height given student in ith column, right? Given the and the sum is from I equals to 1 to 8. So that is exactly what I am doing here. This is the conditional expectation, and when I take this, multiply it by probability and take the sum, that is basically I can write as expectation of the conditional expectation, right? So So this is the conditional expectation, and when I multiply it with probability, take the sum, this is basically nothing but again expectation. So this whole thing is nothing but expectation of the conditional expectation. So what we have done in the school level, we got this one, and what now we are doing, writing this way, is nothing but the generalization of this one, in the sense that in this case I have only finite division of the population, that the column 1, column 2, column 3, but when I am writing in the expectation form, I may have infinite division of the population. Also, x, y can be continuous, can be discrete, all those kind of things come into the picture. But in this example, clearly x, the height is continuous, but y, the column, the number of column, the ith column, that is a discrete. Okay, that is a discrete number. So that means basically this theorem is basically the generalization of this one, and this theorem basically tells us that the overall expectation of x, which is the overall expectation, can be found by computing the expectation of different parts, which is the conditional expectation, by computing the expectation of different parts, and then accumulate all the conditional expectation using the weighted average, or using the another step of expectation with respect to y. Okay, clear? So I hope this that intuitive idea of this one is very clear with everyone. So this expectation is basically nothing but I divide the whole population into sub parts. I compute the expectation in every part, which is the conditional expectation. Then I take again another expectation over the conditional expectation to get the expectation over whole population. Okay, and the proof of this theorem is very simple. So we'll prove it for the discrete one, for the continuous one. The discrete one just replace this integration with the summation. So how this proof goes like, well, this one is a function of y, g of y, right? So it is basically expectation of g of y. So expectation of g of y is nothing but the integration from minus infinity to infinity, g of y, density function of y dy. Okay. Now g of y is basically this conditional expectation. So this conditional expectation can be written in this integration of this function. So I write this here. Now just see that this multiplication, conditional density multiplied by the marginal density, this is nothing but the joint density, because conditional density can be written as the joint density divided by marginal density. So that means conditional density multiplied by the marginal density is basically the joint density. And we have proved, because this is the expectation of x. Okay? So proof is simple, but this is a very, very important, very, very useful formula. We can use it to solve many difficult problems. Okay, let us see some examples. Let us see. Okay, before going into more examples, see that for if y is discrete, then when I take the expectation with respect to y, this is outside expectation is with respect to y, that will be a summation. Okay, so y belongs to support of y, expectation of x given y equals to y into the probability mass function of y. And if y is continuous random variable, then this when I try to compute this expectation, this will be integration and the integration of expectation of x given y equals to y into a density function of y dy. Okay, this writing sometimes helps. So I will find out this expectation multiplied by the probability mass function of y. Take the sum in case of y is discrete. In the case of y is continuous, I will find out this conditional expectation, multiply it with the marginal density function of y. Take the integration. One point, and another point here I should mention here is that, see, we basically, when we talk about expectation, we basically assume the random vector is either discrete or continuous. So that means when I talk about this one, I can we have done, we have to take that this x and y is either discrete or continuous. The x and y as a vector is either discrete or continuous. But this formula can be used not only for discrete, not only for continuous. That x can be discrete, y can be continuous, x continuous, y discrete, all such combination can be possible. Okay, and some example we will see of this nature, and so the exact definition and all those things I am not giving, but when you do the applications, when you do the examples, you will see that the computation of those expectation and all those things very intuitive, very meaningful. Okay. So let us take example. So the first example, suppose Virat is reading two books. Either one is probability books and another is history book. And which book he is going to read is completely random. That means that he can read the first book, the probability book with probability half, and the history book with probability half. And suppose the number of misprint in a chapter of the probability book is having a Poisson distribution with mean 2, and in the history book again a Poisson distribution with mean 5. Okay, clear? The problem is clear. Now, what I try to find out, what is the expected value of misprint that we are going to come across. Okay, so now notice that if I know that Virat reads the history book, then the expected number of misprint is 2. So if I say x is the number of misprint, then the expectation of x given y equals to 1, y is basically 1 if he reads the probability book, it is 2 if he reads the history book. So expectation of x given y equals to 1 is basically 2, and expectation of x given y equals to 2 is 5. Because these are the conditional expectation. 2 is the conditional expectation that number of misprint, the conditional expectation of misprint given he reads the probability. 5 is the conditional expectation of misprint given he reads the history book. Okay, so and what we want to do? We want to do the overall mistake. What are overall expected number of overall mistakes? So that means we try to compute expectation of x. Now I am going to use the previous theorem that I want to write expectation of x, which is expectation of x given y. Because y is a discrete random variable, that expectation is nothing but expectation of x given y equals to y multiplied by probability y equals to y plus expectation of x given y equals to 2 into probability y equals to 2. These two probabilities are given, these two expectations are given. Also these probabilities are also given, plus them in, and finally we got that the expected number of misprint that will come across is 3.5. Okay, so in this case that computation become very simple given the conditional expectations and marginal probability. Okay, we will see many more some other examples, and there are many examples in the problem sets also. So we will come to that, but before that let us see the theorem 3.25. Okay, what theorem 3.25 says? Theorem 2.35 says that if I try to minimize this function, minimize this expectation with respect to any function f, then this function f turns out to be the expectation of x given y. Okay, just recall one thing. When we do the random variable, not the conditional one, when we do the random variable, what we have seen is that expectation of x minus mu whole square is less than equals to expectation of x minus a whole square. Mu is expectation of x. Okay, we have seen this one for all a belongs to R. And in this case, the interpretation we have given that this quantity you can see as the average square distance from x to a constant a. Okay, and this average square distance is minimum when I take a equals to expectation of x. Okay, so in this way expectation of x is the best estimate of x. Clear? That's what we have done. Just recall it. Now in this case also we are doing something of the same nature. See, I am talking about, instead of a constant, now I am talking about a function of y. And if I take a function of y, this quantity will be minimum if the function is nothing but the conditional expectation. Okay, so what does this mean? Again, this can be interpreted as the distance between x and f of y. So now if I sum idea of the random variable y, some information about the random variable y, or if I have information about the random variable y, then the minimum will occur when I take the conditional expectation. That's why given the information of y, the best estimate of x is nothing but the conditional expectation of x given y. Okay, the physical meaning of this theorem 3.24 actually coming from actually generalization of the theorem 2.12. Just cross check 3.1 2.12 once again and come back here. You will understand this one. Okay, so proof is basically technique is again same as before, same as what we did in theorem 2.12, 2.12. So suppose we denote mu y to be the conditional expectation. So we start with this one, this part, then we introduce mu y here, break the square term. Now we will show that this cross product term is zero. Once we can show the cross product term is zero, that means this expectation is same as the sum of these two expectations, and both of the quantities are non-negative because we have square here. So if I now remove this part, then basically this expectation will be greater than equals to this. That will complete the proof. Okay. So now how can I show this cross product term is zero? So only thing now I need to do this cross product term is zero. And how can I show that? So notice that the expectation of this one, again using the previous theorem, expectation theorem. If you say this one is a random variable z, then expectation of z is same as expectation of z given y, right? Expectation of z given y, and now you see that inside the z, this part depends only on y. Now when y is given, this part will act as a constant. So this part will come out of the conditional expectation. So that's what I did, that I write that marginal expectation with respect to y outside, and this part is taken out of the conditional expectation of x given y. So now I try to compute this one, use the linearity property. So I got that the first part gives me expectation of x given y, and second part gives me expectation of mu y given y. The first part, expectation of x given y, is basically mu y, and expectation of mu y given y is basically mu y, because mu y depends only on y, and for given y, mu y acts as a constant, and expectation of a constant is a constant. Okay, so that means I got that this conditional expectation is basically mu y minus mu y, which is going to give me 0, and that's why this cross product term is also 0. Okay, so that completes the proof. Just one thing I mentioned here, it cannot be proved here given what we have done here, but it can be shown that now when this equality holds, equality will going to hold if this part is 0, right? This equality here is going to hold if this part is 0, or if and only if this part is 0, and it can be shown that this expectation is 0 if and only if mu y and mu fy are the same. Okay, if fy is equals to mu y. So that basically this one, this if and only if condition cannot be shown with what we have done here. Obviously, one part you can show that if these two quantity are same, then this has to be 0, but the other one cannot be shown with what we have done. Okay, so that basically means that this function is minimized, this expectation is minimized when I take f of y equals to expectation of x given y, and the equality holds if and only if this f is equals to expectation of x given y. Okay, so with that I stop for this lecture. Thank you for listening.